Hello again, welcome back. This is Terry Collins. The title of this lesson is The Bookcase of Green Chemistry Problems. This is the first part of a two-part sequence. In this lesson, we'll consider that there are two limiting paths forward for green chemistry. We'll examine them and consider their implications. We'll also examine the first three of 6 major classes of green chemistry problems using a bookcase analogy. Two green chemistry paths lie before us as we build this field. The first path deals with hazards that are well understood by chemists and is focused on short-term economic gain. If this is the dominant way for building green chemistry, it will likely lead to a self-contained field focused on problems that are obvious to chemists. Big achievements for sustainability will likely be rare. While it may appear that progress is being made, the field will miss some of the biggest challenges of chemicals to health and the environment. And sooner or later, the wider civilization will become disappointed in green chemistry's performance. The second pathway is built on a synergistic alliance with environmental health sciences and other fields to deal with all hazards, including those not easily understood by chemists. If this is the dominant pathway forward, it will help industry move away from products and processes that are burdened by low-dose toxicities. The field will be characterized by a passion for escaping hazards that most threaten sustainability. It will inspire the wider civilization, leading to sympathy and support for essential industry transitions towards sustainability. And it will bring long-term economic stability to industry. Having a method for categorizing green chemistry challenges is important. We will use the analogy of a bookcase. In this analogy, each challenge is associated with a book that defines a problem in green chemistry, explores its background and history, outlines why an alternative is needed, documents progress, and explores what remains to be done. Related problems will then be collected on the same shelf of the bookcase. Such a virtual bookcase, contains 6 clearly evident shelves and an equator. The bottom 3 shelves fit with the prevailing economic paradigm. We will cover these 3 shelves in this lesson. So here's the bookcase. Notice that there are 3 lower shelves, and then a middle shelf with an equator with 2 descriptors, design for, that apply to the bottom 3 shelves, and design against, that apply to the top 3 shelves. This is the overall shape of our bookcase. On the first shelf, we have the area of design for improvement of synthetic efficiency. This area of green chemistry is alive and well. It's cost favorable for incumbent industry, as many of our major drug houses have found that by reanalyzing their synthetic procedures for major drugs according to the principles of green chemistry, they have been able to develop vastly improved syntheses where they reduce the amount of waste, often the amount of inputs, reduce the amount of hazardous materials involved, and essentially reduce the economic burden on waste management and increase the overall profitability of the drug. An excellent example of this is the drug Taxol, also called paclitaxel. On the right-hand side, you can see 2 pictures of this very complex drug. Taxol is potent against breast and ovarian cancer. It was reported in 1971 from the bark of the Pacific yew tree, Taxus brevifolia. However, it was present only in 0.004% or 4 parts per million. Sales peaked in 2000 at about $1.6 billion per year. Early preparations required stripping of the bark, killing trees that take 200 years to mature. Obviously not a very sustainable process. Published syntheses involve approximately 40 steps with overall yields of about 2%. What this means is that the drug is very expensive if prepared in this way. The pharmaceutical company Bristol Myers Squibb developed a sustainable process using plant cell fermentation, or PCF, which was based on twigs and leaves from the yew tree. The plant cell fermentation approach has no chemical transformations. When the Presidential Green Chemistry Challenge Award was made for this process in 2004, it was claimed that during the first 5 years of use, PCF was to eliminate 71,000 pounds of hazardous chemicals and other materials, 10 solvents, and 6 drying steps, saving much energy. Again, that award was made in 2004. This brings us to the second shelf of the lower three in our bookcase. On the shelf, we have challenges for green chemistry associated with design for renewable resources, basically for renewable feedstocks. Again, this area of chemistry is becoming economic opportunity driven. A classic case in this area is marked by the Presidential Green Chemistry Challenge Award of 2002 to the joint venture of Cargill and Dow that has subsequently become the company NatureWorks LLC. In this case, the chemical lactic acid is converted to a lactide that is then polymerized to give polylactic acid. The lactic acid is obtained by fermentation of plant sugars obtained from corn. Here is a picture of the NatureWorks polylactic acid plant in Blair, Nebraska. Production in this first world-scale 310 million pound per year plant began in November 1 of 2001. NatureWorks' trademark for the PLA product is Ingeo. This brings us to the third of our lower three shelves, Design for Solar Energy Technologies. This shelf also is becoming very much economic opportunity driven. Design work for solar technologies is extraordinarily diverse and spread all around the different areas of chemistry. Certain of these are associated with green chemistry. A classic example is the company Plextronics Incorporated, a Carnegie Mellon University spin-off company that has produced regioregular polythiophene that has a very high photovoltaic efficiency, approximately 6%, for a polymer-based product. This is amazing stuff. You can take a solution of polythiophene and chloroform and spin cast it onto a surface, clamp electrodes on either side, and you have your photovoltaic device. Very simple in the manufacturing of the device itself. Well, imagine now how much better the future might look when more major advances have been achieved and documented in books on the three lower Design for shelves. A few highlights go as follows. The component of synthetic chemistry optimized for health and the environment will be greatly expanded with improved profitability. Numerous chemicals that we need for building the civilization will be obtained from recently dead as opposed to fossilized plant matter, recycling carbon dioxide from the atmosphere in the process. Important new technologies for converting solar to electrical or chemical energy will be developed and deployed. With some good fortune, some of these will be major energy technologies. In the next lesson, we will examine the top three design against shelves and see how the challenges are somewhat different in character from those of the design for shelves that we've just considered.